All right, we're going to talk about explicit rules today. So today we're going to use an explicit rule to write out elements of a sequence. All right, explicit rules are a little bit different than recursive rules. You might remember from Friday that recursive rules are defined in terms of the previous term. So in order to find the next one, I have to know what the one before it was, right? Explicit rules are going to be a little different. All we have to know is the n, and we can use that to find our term number or the term. Okay, so you might recognize some of our friends. Here we've got an arithmetic version and a geometric version. A sub 1 is still our first term. Okay, can you guys focus, please? Okay, what do you think D is? No. I'm literally writing it.
Common difference.
It is the common difference. Okay, so what is our first term in this beautiful example here? If you look. 4. Okay, and then what do I do to get to my next term?
Add 3.
Add a 3. So my next term will be 7, followed by 10, followed by 13. ... Keeps going. So basically the same thing we did on Friday. We just have to know where to look for the little tidbits that we need. We need our key pieces of information. For geometric, we still have G sub 1, which is our first term. And we still have R. What is R?
Common ratio.
Yes, it is our common ratio. That is what we multiply by every time. All right, so what is our first term in this geometric example? What's in the G sub 1 spot? 5. So we're going to start on 5 and then do what to get to our second term?
Times 2.
Okay, times 2.
10.
So 10. And then?
20.
Okay, and then?
40.
40. And so on. Easy peasy, lemon squeezy. Okay. So on this next example, this matching example, I have for you a whole bunch of sequences. They are arithmetic, they are geometric, they are recursive, they are explicit, all in a big pile. Okay? So you can use your pink sheet. Okay, I'm talking about this one. This one has all of the types on it. Remember, it goes ER, ER, right? Oh, Old MacDonald. Old MacDonald wants an A. ER, ER, O. All right, you're matching. Did you do it already? You matched them up? Okay, so we're not going to tell them because they're still working. But on this one, we're multiplying by 2. Okay, so that's this R value. R is 2, so that's C. Okay, this one, we're subtracting 0.5. Okay, that is this one here where D is negative 0.5 or negative 1/2. So this is D. On this one, we're adding 6. Okay, so that's this one where D is 6. That's A. And last but not least, this one, we are multiplying by 1/2. which is an r value of 1/2. That's this guy. So this is b. So it's not just enough to say anymore going down by half, because we could be subtracting a half every time, or we could be multiplying by a half every time. Either way, we're decreasing. Do you understand what I'm saying? So we have to be very specific with our language. How did you guys do? Did you get them right?
Yes.
Okay. Good. They're very smart. All right. So now we have to use the explicit rules to write the first 4 terms of each sequence. This is the same thing that... Could you stop distracting me in class, please? Okay, stop looking at him. The show is up here, and you're wasting everybody's time. All right, so we want the first 4 terms of each sequence. So what do I start at?
17.
Yeah, my first term is 17. To get my next term, I do what?
Subtract 6 and
Okay.
11.
11, then
5.
then
-1.
-1, and I'm done. All right, go over here. What do I start at? 2, and then do what?
Multiply by 3.
6, and then
18.
and then
54.
whoop, you're right. Good. So basically the same thing we did last week. Now, this is where it gets exciting, because there are 2 ways to do this one, and last week we only had 1. And this is going to tell us the difference between explicit and recursive rules. So let's start with the way that we already know, okay? That's to make a table. You guys remember this?
Yes.
Because we have to find the n. So we're going to make our table of n's and a sub n's. Hey. Okay. What is my very first term?
12.
12. What is n for my first term?
1.
1. And then I have to add 5 to get 17, which is term 2. And then term 3 is 22. 4 is 27. 5 is 32. 6 is 37. Almost there. 7 is 42. 8 is 47. Okay, so that's how we had to do it last week. There was no other way to find that 8 was our n. Now, that was because we had a recursive rule, so we needed each previous term to find our next term. Okay? An explicit rule is defined by n. So this makes it very much like a function which is defined by x. Okay, so we're going to treat n's like x's and a sub n's like our y's is what I'm trying to say. Sorry. So if we want to find n, that's our input. Okay, it's kind of like our x, right? And if we have a value, that is our a sub n. It's our output. Okay, it's like our y. It's the analog to our y. So we're going to use our rule, and we're going to plug in our stuff. Okay, write small. So a sub n is 47. 47 equals, do you see where I'm plugging it in right here? 47. 47 equals 12 plus 5 times n minus 1. How are we going to get rid of parentheses? Yeah. So now I have 47 equals 12 plus 5 minus 5. Oops, 5n minus 5. Like, that doesn't look right. Do we have some like terms to combine?
Yes.
Okay, so 12 minus 5 is
7.
Okay, 7. So I have 47 equals 7 plus 5n. Can you subtract 7 from both sides in your head? 40 equals 5n. Can you divide by 5 in your head?
No, you get 8.
Yeah. Shocker.
That's great.
Isn't that crazy?
Yeah.
So we couldn't do that with a recursive rule, otherwise I would have showed it to you. I wasn't holding out on you.
We're still allowed to do the table though,
We're
right?
still allowed to do the table. The advantage of this other way is, like, let's say that I gave you some obnoxious number like 257. Would you really want to make a table that goes all the way out to 257? It ends up being faster to do this at a certain point. Does that make sense? Okay. Cool. All right, let's look at example 4. So we have to find the fourth term. So we don't really care about the first 3. We just want the fourth one. So we can start at what? 36 and do what?
Times 1/2.
Times 1/2. So that would be 18. And then half of 18? 9. Half of 9?
3 times 4.5.
4.5. So this is the only one we care about. We only care about g sub n being 4.5. Okay, the answer isn't all of the first terms. It's just the fourth one. You see the difference? Okay, next one. Now, we can either do it like this, where we list out the four terms, and we just care about the fourth one, or we can remember that we can treat this like a function, okay? If we want term 4, what is our n? If we want the fourth term, term number 4, what is our n? 4, right? So this means that our n is 4. So watch this. A sub 4 equals, I'm putting in a 4 wherever I see an n. A sub 4 equals 25 minus 3 times 4 minus 1. What's 4 minus 1? 3. So A sub 4 equals 25 minus 3 times 3. What's 3 times 3?
9.
Yeah. Okay, 25 minus 9. Yeah. Oh, I did minus. It's supposed to be plus. Would you guys help me fix that? It's supposed to be plus. What's 25 plus 9?
34.
Yeah, 34. So A sub 4 equals 34. Now, that might seem like more work, but let's say that I asked you for like the 1,000th term. Would you want to make a table way out to 1,000 terms? No. Wouldn't it be easier just to plug in 1,000 and simplify really easy on your calculator? Just saying. Okay, do you want to practice making a table for this one really quick? For a list? So we start at 25, and then we do what? Add 3, so 28, and then 31, and then 34. So either way, we get A sub 4 equals 34. Questions? All right. Do we need to do another one of these or are we good? It's like the last one we did on the front. Are we good? Speak now or forever hold your peace. All right, let's do the Daffy problems. Can we have the humming end? Thanks. Okay. So poor Daffy has been trying to do these sequences again. He's trying to write rules. Okay, what is his first term? Oh, he's writing explicit rules. Okay, because that was the title of our notes today. So what is his A sub 1 here that he was given? 7. Okay, what's happening every time? Add 3. So is it arithmetic? Okay. So can you figure out what's wrong with his rule? Use your pink sheet. Is his A sub 1 correct? Is his D correct? Then what's wrong with this rule? Is it explicit?
Oh no.
What kind did he write?
He wrote recursive rule.
Yeah, he wrote a recursive rule. So we have to fix it. He didn't follow directions. So he was supposed to do that, explicit. All right, so use your pink sheet. Okay, how do we define A sub n? A sub n equals A sub 1. Okay, do you see how they have D written in the back? Okay, isn't 2 times 3 the same as 3 times 2? So it doesn't matter if you put the D behind the parentheses or in front of the parentheses. I prefer to see it in the front. Is that okay with you guys? So I'm going to write the D in front of the parentheses, but you could write it in the back. It doesn't matter. Except that I think it looks awkward if you have like a -2 that you're multiplying by, and if you forget the parentheses, then it looks like subtracting 2. So I don't like it written in the back. I like it written in the front. Okay, so now we just have to plug in the 7 and the 3 in the right spots. So the 7 is going to be the A sub 1, and the 3 is going to be the D. So we just copy that down. A sub n equals 7 plus 3 times n minus 1. It's easy enough. All right, what about this one? Okay, starts at 5, and what's happening? Oh, times 3. So is it even arithmetic? It's geometric, so let's change that for Daffy. So it looks like Daffy only looked at the first 2 terms of the sequence where we added 10, and so he assumed it added 10 every time, but it's actually multiplying by 3 every time. So he wrote an arithmetic rule for a geometric sequence. Okay, let's fix it. So if I look at my formula sheet, okay, my explicit geometric rule is G sub n equals G sub 1 times my R to the n minus 1 power. So I just have to figure out what my first term and my r value are. So I already know that my r is 3. What's my first term? Five. So in the g sub 1 spot, I'm putting a 5. In the r spot, I'm putting a 3. So g sub n equals 5 times 3 to the n minus 1 power. Do you see how the n is in the power, just like x is in the power of an exponential function? You can see that this even looks like a function rule, input, output. I think that we don't maybe need to do the last matching problem. I think we could be done. Are we ready to be done? Okay, you guys did good.